Good afternoon, everyone. Welcome to the class of antenna and wave propagation. And the today topic is the fundamental parameter of antenna. And one of the two parameters we'll discuss, that is the radiation pattern and the beam width. I'm Himanshu Nagpal, assistant professor in EC department of AKGEC Ghaziabad. These are the fundamental parameters of the antenna. First one is the radiation pattern, and another parameter is the radiation intensity, beam area, directivity and resolution, gain, beam width, effective aperture area, and the antenna temperature and the antenna impedance. Today we will discuss about these two parameters, radiation pattern and the beam width. So to start with the fundamental parameters of antenna, first we will just describe or briefly describe the mechanism of the antenna in a very quick time. That antenna is a transducer which converts the electrical energy into the electromagnetic waves. It is a transducer which converts one form of energy, that is electrical energy, into the electromagnetic energy, and this will be at the receiver and at the transmitter side. And at the receiver side, this electromagnetic energy which is received at the antenna will be converted into the electrical energy. So you can say that this antenna converts electron to photons or vice versa. The basic principle behind the radiation is that the radiation is always produced by the accelerated or deaccelerated charges. When there is a movement of the charges in the transmission line or the antenna, and these charges are either accelerated or deaccelerated, then only the radiation will produce. A stationary charge will not radiate, and neither does an electric charge moving at uniform velocity along a straight wire. If there is a straight wire and uniform charge, a stationary electric charge will be there, then this wire will not produce any radiation. Or you can say, if there is an electric charge moving at a uniform velocity, then also there will be no radiation. So for radiation, the charge moving at uniform velocity, if a charge is moving along at uniform velocity, then there should, for radiation, there should be the wire should be bent or curved wire is, and then when there is a bending of the wire or there is a curved wire, then there will be a change in the velocity of charges, and the wire will and the charges will get accelerated or deaccelerated, then only the radiation will produce. So mainly for the radiation, wire should be bent or discontinued at uniform velocity of charges. Or you can say that if there is a acceleration in charges, then also radiation will be there. Clear? So only accelerating charges produce radiation. So there are three types of radiators antenna. First one is the isotropic radiator, omnidirectional radiator, and the directional radiator. Isotropic antennas are the antennas, or isotropic radiator is the radiator which produce this topic will also covered in the radiation pattern also. This isotropic antenna which produces radiation of equal intensity and in all direction. Okay, So this type of antenna is known as the isotropic antenna. This omnidirectional is the antenna which produces the radiation in all the direction, but you cannot say there will be of equal intensity. Clear? And this directional antennas are the antennas which produces the radiation in a particular direction. Means whole of the energy radiated by the antenna will be in the particular direction. So this is a basic, for a brief review, this is a basic equation of the radiation equation, that is di by dt multiply में L is equal to Q into में dV by dt. This I is the time changing current, L is the length of the current element, Q is the charge, V is the time change of velocity which produces the acceleration, ठीक है, and L is the length of the current element. So it simply states that these are the conditions for producing a radiation, that it simply states that to create radiation there must be a time varying current or acceleration of charges, or to create a charge acceleration the wire must be curved, bent or discontinued or terminated. The wire should be bent, means if this is a straight wire and there will be a uniform velocity, straight wire with a uniform velocity, then no radiation will be there. But if this wire is curved or bent, then radiation will be there. So this wire will be act as a antenna. So periodic change, acceleration or deceleration or time varying current is also created when charge is oscillating in a time harmonic motion. Therefore, if charge is not moving, the current is not created, then there will be no radiation. First condition is that if charge is not moving, means there is no current and there will be no radiation. Second point, if charge is moving with uniform velocity, then there are two conditions. There is no radiation if the wire is straight and infinite in length, and second is there will be a radiation if the wire is curved or bent or discontinuous. Clear? Third point, if charge is oscillating in a time motion or time varying current will be there, then it will radiate even if the wire is straight, because there is a charge is oscillating, and means when charge is oscillating means there is a time varying current, or you can say there is a acceleration or deceleration of charges. So this is the basics antenna. First, this one is the source. This source produces a electrical signal, and this electrical signal is getting modulated and it passes to the antenna through a transmission line, and this antenna is a transitional structure which converts what? Electrical signal into the electromagnetic waves, and these are the free space which is radiated into the space, and at the receiver side these waves when gets into the far field region, these EM waves converted will be transformed into the planar waves, and these planar wave when incident at the receiver side, it will produce what? Electrical signal. EM waves will be converted to the electrical signal, and this is the receiver. So if I say this is the transmitter or the receiver, this is a transmission line, and this one is the antenna, then there will be some resistance will be there, that is known as the radiation resistance. This radiation resistance which mainly couples with the impedance of the, this radiation resistance mainly help in the impedance matching between the antenna terminals and the free space impedance. Let's say if this radiation resistance is helpful in impedance matching, when there is an impedance matching between the antenna terminals, impedance at the antenna terminals with the impedance of the free space, then only the radiation will be produced in the space, otherwise radiation will not produce in the space and it will get back into the transmission line and produces a standing waves. Clear? So from the circuit point of view, the antenna appears to be a transmission line as a radiation resistance. This is called as a radiation. It is not related to any resistance the antenna. It is not related to the antenna resistance, but itself is a resistance coupled from the space to the antenna terminals. Clear? So you can see here that basic transmission of basic mechanism of antenna, how antenna radiates. Let's say this is a source which provides a electrical or voltage to this transmission line. When there will be a charges present inside this one, when there is a positive cycle or negative cycle. When there is a next cycle, then here will be a negative charge will be there. At the another cycle, there will be positive charge, negative, positive. When there is positive charge here, negative charge will also automatically produce in this here. And when this is a positive and negative charges, the electric field will move from positive to negative terminal. These are the direction of electric field, and this combination of positive field, positive charge and negative charges produces a what? Current. And this current, when there is a flow of current in this transmission line, there will be a magnetic field will also be there, which is perpendicular to this electric field directions. So in the next cycle, these are the positive charges. These positive charges, electric field direction will be from positive to negative terminals. Similarly, this at the antenna transitional, where the impedance matching will take place. So at the end, these are the electric field directions. So when at the end, during the detaching of this antenna terminals, these field will get detached into the free space, and here is the positive. The next will be what? Here positive direction will be there. So these are the direction of the. Now when there will be negative cycle changes, these direction, these waves, these electric charges is converted to electromagnetic waves and get detached into the free space, and the another cycle will be formed. Here will be, then here will be, these are the electric field lines will be produced. Clear? So this is the how antenna radiates. Now next one is the one of the fundamental parameter of the antenna by which we can determine the characteristics of the. This is an important parameter by which we can determine the characteristics of the antenna. First one is this is the radiation pattern, and this radiation pattern is defined as the mathematical function, graphical representation of the radiation properties of the antenna as a function of space coordinates. Let's say if I say this is the antenna, and this antenna produce radiation in the whole space. So the radiation will produce in the whole space or in some particular direction, means there will be some graphical representation will be there, when I can say that at what intensity this antenna will produce in this direction or in this direction or in this direction. So there will be a graphical representation of the what? Radiation properties of antenna as a function of space coordinate system, means as a function of what? R, theta, phi. Means at this direction there was some location of coordinates, means R can be 5, theta can be 80 degree, phi can be 90 degree, 170 degree. Clear? So at this point there is some R, theta, phi. So at this point how much radiation will produce, and at this point how much radiation will be produced. So so radiation pattern determines or gives the graphical representation of the radiation proper of antenna as a function of a space coordinate system. In most cases the radiation pattern is determined in the far field region. Now we always determine the radiation pattern in the always in the far field region and is represented as a function of the directional coordinate system. Or you can say that once the EM waves leaves the antenna, once the EM waves, this is the antenna, once the EM leaves the antenna, the radiation pattern tells us how the energy propagates away from the antenna. This will tell us how much the energy, how the energy propagates in the space, means how the energy, whether this energy produced in this direction, in this direction, in this direction, or in this direction, in any direction, and with what intensity it will be propagated in the space. So radiation pattern tells us about this one. So radiation pattern is the three-dimensional quantities involving what? Variation of field, how many field, electric field in this direction will be different, electric field direction, electric field in this direction will be different, electric field in this direction. So this tells us about the variation of field or power, which is proportional to the square of the field. Clear? As a function of what? As a function of what? Spherical coordinate system, that is r, theta and phi. So let's say this one is the three-dimensional radiation pattern. So you can see here that this, and let's say this antenna is placed here, and this antenna produces the radiation in this area. Clear? This antenna produces this in this area, and these are the side lobes, which gives the small amount of energy. This antenna produces small amount of energy along this direction. So the most of the energy electric field energy is concentrated in this direction. So this one is the, we can say, major lobe of antenna, where most of the energy is concentrated, or this, we can say this is a major lobe or the main lobe. The energy is concentrated, some energy is concentrated some low energy is concentrated in the other direction. So low energy which is concentrated in the other direction, these are known as the side lobes. These side lobes are, or can be of, say, two types, that is minor lobe or back lobes, or you can say other lobes. Clear? Let's say so how can we say that if I want to represent this radiation pattern in two-dimensional figure, so you can see this radiation pattern can be represented in two-dimensional figure like this one. And these are the this one is the major lobe, which represent this area. These are the side lobes. These are the side lobes. Clear? And this one is will be a back lobes, which is opposite to the main lobe. Clear? And this is what, at which there will be a theta equal to 0 degree will be in this direction. theta will be 0, will be in this direction. Clear? Now see, if I want to calculate the electric field at point P, if I want to calculate the electric field at point P, then I should know the r, theta, phi. So let's say if I want to calculate the electric field at this point P, this is point P, r will be what? Let's say the original antenna is placed here, so this will gives the direction of r, and phi will be, let's say at this point, this phi transformation of this point will be in the xy plane, will be this direction, and this will give the phi, and this phi will be, let's say this phi is 85 degree. So r will be what? Let's say 5, r will be this one, phi will be, take the transformation of this point at the xy plane. So this will be the transformation of this point in the xy plane, and measure the phi in the anti-clockwise direction from the x-axis, so positive x-axis. So phi will be 85 degree, and theta is the angle between this point P from the positive z-axis, angle between this point P to the positive z-axis, this gives the theta. If I say this is theta equal to 30 degree, the location of this coordinate of this point will be r, it is from the origin, it is distance 30 degree, 85 means at this point, if I want to calculate the electric field intensity or electric field, so this is the radiation pattern. So radiation pattern have some parameters. In this we can determine the major lobe, minor lobes, and back lobe, or you can say side lobes. This is mainly side lobe. These are the side lobes, major lobe and side lobe. These side lobes consist of minor lobe, other lobes, and the side lobes. Oh, sorry, back lobe. Clear? So this radiation pattern can be written in a two-dimensional figure, can be drawn in as a two-dimensional figure like this one. So most of the energy concentrated in this direction, in the upward direction, when the theta is equal to what? 0 degree. So most of the energy is concentrated in this direction. So this one is known as the major lobe. Generally we always take the major lobe. In the at theta when we equal to 0 degree. These are the energy concentrated, energy flow or radiated in these all other directions other than the major lobe are known as the side lobes, and these side lobes is further categorized into three parts, that is minor lobe, the lobe which is next to the major lobe in the intensity level, that is known as the minor lobe, and the lobe opposite to the major lobe is known as the back lobe, and rest are known as the other lobes, you can say, or you can also say that these are the side lobes. Clear? and the area where no radiation is produced, this is the area where no radiation is produced. This is the area where no radiation is produced, where no radiation is produced. These are known as the null. Clear? So from the above figure, from this figure you can see that this is a three-dimensional figure pattern with radius r from origin to the pattern boundary is proportional to the field intensity in the direction of theta and phi. The pattern has its major lobe in the at theta equal to 0 with minor lobe in other direction. Means you can say here major lobe is in the direction theta equal to 0 and the minor lobes are in the other directions. Okay. Now the direction of the P point is at the angle theta equal to 30 degree and phi equal to, so this one is the direction of P, where this one is the R and this one is the theta, that is equal to 30 degree, and this one is the phi. The transformation, if I take this point P, transformation in this xy plane, so this direction will gives you theta equal to phi equal to 85 degree. So this one is the three-dimensional view of the radiation pattern. Let's say this one is the dipole, this is a dipole, and this dipole is, if I provide this dipole a current of having charges, whether it will be acceleration or deceleration or current varying, time varying current is given or supplied to this wire. So this is known as the dipole antenna, because this current, this wire will act as a dipole because I am providing a time varying current to this wire, and this will produce a radiation. That depends what is the length of the antenna, whether the length of the antenna determines whether this antenna is known as the dipole, Hertzian dipole antenna, Hertz dipole antenna, current element, or you can say. So if I take that radiation pattern, how the radiation is produced from this antenna will be like this one, you can say, in three-dimensional figure. So this antenna, you will see here, this antenna produces energy in all the directions, but at this point, the radiation is very less. You can see here, at this point, there is some null will be there. So this antenna, we cannot say this is an isotropic antenna, because it produces the radiation in all the direction, but at this point, the radiation will not be, there will be no radiation at this direction. There is a null. So that's why I cannot say that this is a isotropic antenna. So for an antenna, from the radiation pattern, I can measure the radiation pattern can be of two types: field pattern or the power pattern, or the power pattern decibel. Let's say if I say this is a radiation pattern, let's say these are the three patterns. This pattern will be known as the field antenna in linear scale when this represents what? Electric field intensity. When this represents the field intensity in a linear scale. So this type of pattern is known as the field pattern. Now this radiation pattern will be known as the power pattern in linear scale when this scale, this axis This axis shows what? Power in linear scale. Means you can say power in, let's say power in 1 milliwatt, 2 milliwatt, anything. Clear? And this radiation pattern can also be known as the power pattern when it represents what? When it's represented power in decibel form. Clear? So this field pattern represents the plot of the magnitude of the electric field or magnetic field as a function of angular space. Electric field, magnetic field as a function of angular space, because this is theta. Clear? This pattern is power pattern, typically represents the plot of the square of the magnitude of the electric field. Means square means this is power, or you can say it is equal to E square, or you can say H square. This is known as the power pattern linear scale, and this power represents the magnitude of the electric field in decibel form. Means this power represents in decibel form, that it is known as the power pattern. So when if I want to calculate the normalized field pattern, always divide the electric field intensity at that location. If I want to calculate the, let's say if I want to calculate the electric field intensity at this point P, normalized electric field, so there will be some electric field intensity at this point theta at this location. When it is divided by the maximum, this maximum E theta phi max, this will give the normalized field pattern. Similarly, normalized power pattern will be when it is divided by the maximum power. So next topic is the beam width. Beam width is the angular separation between the two half power point. It is known as the half power beam width. Next, this is the next fundamental pattern, one of the fundamental parameter of the antenna, which determines the characteristics of the antenna, whether the beam width is very narrow or high. This is mainly concentrated when the antenna is used for satellite or defense purpose. This parameter is mainly used or mainly important for the antenna, which is used for the satellite communication or the defense purpose. So the angular separation between the two half power point is known as the half power beam width, and the angular separation between the first two nulls is known as the beam width between the first null. That is, if I say this is a radiation pattern. Clear? The maximum power is concentrated in this direction at theta equal to what? 0 degree. Let's say this is P in what? In milliwatt scale. Clear? This is power in milliwatt, you can say. If I want to say this represents the power in dB, and if I say this is another radiation pattern, or you can say field pattern, this represents what? Electric field intensity at theta equal to 0 degree, and this will be generally it will be a Emax. So half power beam width, angular separation between the two half power points. It means what? Let's say this is maximum field is equal to let's say this is P maximum. So two angular separation between two half power points. This, when there is a point, there will be some point where the power will be what? There is some direction at which power is what? Half of the maximum, that is P by 2, and there is some point in this direction also. So angular separation between these 2 points, this shows what? This shows the half power beam width. Clear? Now, but when I say this power is in decibel, so half power beam width is what? Let's say this is equal to 7 dB. In case of half power point when it is decibel, just there is some point when there is 7 dB minus में 3 dB, means there is some point that is equal to 4 minus 7 minus 3 dB equal to 4 dB. So there is some point where the power will be 4 dB, and in the also there is some power will be in the 4 dB. So these points are known as this angular separation between the 2 points is known as the half power beam width. Now, when it is case in the electric field, let's say this is E max equal to 1. So there is some point where this is electric field is equal to E max divided by root 2. Clear? And here also there is some point. This is known as this angular separation between these 2 points is known as the half power beam width. Now, next one is the angular separation between the first 2 nulls. This is radiation pattern. First null is here, this one, and the here from, if I say from moving this side, first null is this one, and from moving this side, this is the first null. I have already told you what is the null where no radiation will take place. So the angular separation between these 2 nulls, this angular separation between the 2 nulls gives what? First null beam width between the first null, or your first null beam width. Clear? Similarly, this is the first null here, and this is the first null. So angular separation between these 2 is known as the first null beam width, and here this is the first null and this one is the first null. The angular separation between these 2 gives the first null beam width. These are the, I have already told you, field pattern. This is where the 0.707, if I say this is a power pattern in linear scale, this is 1, 0.5, 0.5, the angular separation between these 2 points is known as the, clear? So these are the lobes which I have already told you, major lobe, minor lobe. What is the isotropic antenna? Antenna which radiates energy in all the direction with equal intensity, that is the isotropic antenna. A direction antenna is the antenna which radiates or receives the electromagnetic waves effectively in some direction, then in the, that is known as the direction antenna. And the omnidirectional is a special type of antenna, directional antenna, where I have already do this one, this type of radiation will be there, means there is some null will be there. So this type of antenna is known as the omnidirectional antenna. These are the topics we will discuss in the next class. So book which I have referred for preparing these slides is the Antennas by John D. Cross, J.D. Cross, and another book is the Antenna Theory, Analysis and Design by the C.A. Balanese. Thank you.